From the Library of Congress in Washington, D.C.
Good morning, and welcome to the final NASA Goddard lecture for 2014. And this is the conclusion of our 8th year of these programs. And we will be back in 2015 with more. We're now getting our ideas together and our wishes and asking what NASA has to offer us, and they're always fabulous, so we really enjoy this collaboration. I'm Stephanie Marcus from the Science, Technology, and Business Division. And our program today is measuring our underground water supplies from space. Nobody can argue about the importance of water or underground water. So today we're going to learn about advances in measuring and monitoring that vital resource. Our speaker today is Matthew Rodell, who is chief of the Hydrological Sciences Laboratory at NASA Goddard Space Flight Center. Dr. Rodell earned a BS in Environmental Science at William & Mary and his PhD in Geological Sciences at the University of Texas at Austin. And he tells us that his wife is a geologist who also studied in Texas, so that's where that partnership came from. He has already garnered many honors in his career, including a Robert H. Goddard Award for Exceptional Achievement in Science back in 2011. He's an associate editor of the Journal of Hydrology and has authored more than 60 peer-reviewed publications in various journals. I'm not going to go on about anything else because we want to hear what Dr. Rodell has to say, so please join me in welcoming him to the Library of Congress.
Thank you, and I appreciate such a nice introduction. My first slide is actually, quick biography. I think it's always useful in a situation like this to know a little bit about the speaker. So yeah, you said a lot of this stuff. I grew up in Connecticut, moved around quite a bit. I went to college in Virginia at William & Mary. That's actually where I met my wife. She was the geology major at the time. She's a much better geologist than I am. I loved environmental geology and hydrogeology were my two favorite courses, and had sort of a mentor teacher there, and so he sort of helped me get started in hydrology and helped me get my first job, which was in New Jersey, driving all around the state of New Jersey to HES stations and taking samples of their underground, their aquifers, and just to see how far the underground storage tank leaks had spread. And so if you're not aware of that, I mean, a lot of the older stations, gas stations in the U.S., they have these underground storage tanks that used to be single-walled, and they would eventually rot out, and the gas would just get into the ground and seep slowly through the soil. And if there's no better, if they don't have a real financial reason to do something about it, they're just going to monitor it and try to keep this plume on site. And so that was sort of my job, was to take these measurements in wells and see how far the gasoline had gotten. So I was there for a year, and then I was happy to get back to school after that, and got my PhD at University of Texas at Austin in geology. And my supervisor was Jay Familietti. So if any of you saw the 60 Minutes 2 Sundays ago, talking about groundwater and a lot of things I'll be talking about here, Jay Familietti was on there. He was my PhD supervisor, and we're still close collaborators and friends. And actually, he's in the movie The Last Oasis. Have you ever seen The Last Oasis? It's a good movie about water. He stars in that. So currently I'm the chief of the Hydrological Sciences Lab at NASA Goddard Space Flight Center, which is just up the road in Greenbelt, Maryland. And my lab does remote, NASA has a lot of remote sensing assets, meaning satellites, and we do remote sensing and numerical modeling of the water cycle. So, some people don't realize that we have, Earth Science Division at NASA, and wonder why does NASA study hydrology? Shouldn't you be working on Mars or stars or something? Well, there are a lot of good reasons, actually. Just going through some of these congressional reports here, the Western governors, or not congressional, these national reports. The Western Governors Association in 2006 says that no other effective climate disruption is as significant as how it endangers already scarce snowpacks and water supply. The Office of Science Technology Planning in 2007 said 39 U.S. states anticipate some level of water shortage within the next decade. That's turning out to be true. This was the National Research Council's report, which is sort of a guiding document for NASA on what satellites they should launch, and basically says that we need an observing system that uses space-based instruments. This is a federal interagency panel which says, in a report to Congress, says today there's a need and an opportunity to modernize hydroclimatic data networks and climate-relevant data collection, data management, mapping, modeling, and information dissemination. Of particular importance is maintenance and strengthening of long-term in situ and remote observation capabilities to detect change. And this is an intelligence community report in 2012. So you can sort of see this building where this is, you know, it's not just scientists saying these things about climate and water. I mean, there's a real recognition in the business community, intelligence community, military that these are all important issues. So the intelligence community in 2012 in their assessment says during the next 10 years, many countries will experience water problems, shortages, poor water quality, or floods that will risk instability and state failure, increase regional tensions, and distract them from working with the U.S. Between now and 2040, freshwater availability will not keep up with demand absent more effective management of water resources. Water problems will hinder the ability of key countries to produce food and generate energy, posing a risk to global food markets and hobbling economic growth. Finally, our strategic plan for NASA includes an objective to advance knowledge of the Earth system as a system to meet the challenges of environmental change and to improve life on our planet. So, hope you're satisfied that I should be doing work for NASA studying hydrology. What does NASA do exactly? We develop Earth observation systems. So if you think about a lot of the remote sensing systems, the satellites that we have that the Weather Service uses to give us weather reports, and many of those were developed by NASA, and then there's supposed to be a transition to operations, so we're developing all these new technologies. What's supposed to happen is we develop these technologies and then pass them on to NOAA or another operational agency, and they continue to launch new versions and continue to keep this thing running, so we have a long-term record. Unfortunately, a lot of times the money's not there to make that transition. NOAA says, well, we don't have any more money to keep doing this. So there's a real question of who is supposed to, once we've determined, you know, this is a really important observation we should continue to make, well, who's gonna do it? That's the real hitch here, the real problem we've had. NASA also helps to interpret the satellite observations, and we also use them for various socially relevant applications. So I'm a hydrologist. I study the global water cycle, which is the continuous movement of water within, on, and above Earth's surface. And so this is a simplification of the global water cycle, and basically, you probably all know what it is, but you basically have a net movement of water from the ocean into the atmosphere, and net movement of water over the land. Some of that water falls as rain or snow and becomes part of our terrestrial water storage, which is the soil moisture, surface water, groundwater, and snow, and eventually either runs off back into the ocean or evaporates. And so this continual movement is the water cycle. These are recent estimates of the size of these fluxes from a study that I led, and using mainly satellite observations. And these fluxes are in units of thousands of cubic kilometers per year. So let's see, the Lake Michigan holds about 5,000 cubic kilometers of water. So looking at some of these fluxes here, so the amount of water that runs off from all the continents into the ocean each year is about 9 times the volume of Lake Michigan, and you have an equal amount of water coming, from the ocean into the atmosphere. So these two balance out, and so these are just huge fluxes. Is the point. The other point I want to make in this slide is that if you think about climate change, some of the most noticeable impacts of climate change will be impacts on the water cycle. Water's so vital, obviously. So that was a simplification of the water cycle. Obviously, there are a lot more components to it. This is from a science paper that sort of tries to estimate some of those other components. But there are things like domestic water uses, how much water do we use for irrigation, and obviously you can divide the surface water into wetlands and rivers and surface water. You can divide rainfall into, precipitation into snow and rainfall. So this is a very complex cycle, and it becomes even more complex when you think about it on multiple spatial scales and time scales. Distribution of water on Earth, apologies, it's a little hard to read some of these numbers. So 97.5% of the water is in the oceans, leaving about 2.5% fresh water on Earth. Of that, 2/3 of it is stored in glaciers. What's left is largely groundwater, the water stored underground. The surface waters in the atmosphere are only about 0.4% of the water on Earth. In terms of freshwater usage, agriculture is the biggest use by far. It uses about 68% of our freshwater usage. There's also domestic and industrial uses. Power is about 10%, and then there's some evaporation. But if you look at the consumptive use, which means you use the water, so a non-consumptive use would be something like power generation, where they're just using the water to cool something off, and then it's going back into the river or whatever. So you're not actually, that water's not gone. A consumptive use would be irrigation, where most of the water, when you irrigate, is going to evaporate, and then you can't use it again. It's gone to the atmosphere and it's back into the water cycle. So for consumptive uses of water, agriculture is 93% of our water use. So how do we monitor the water cycle? If you're going to do it with conventional ground-based observations, it's pretty labor and cost intensive. So this is a SNOTEL station up in the mountains in Colorado, and so you imagine, not only, first of all, you got to get up here. Okay, this is often, they try to get these things up in isolated areas in the middle of nowhere. So you got to get up here with all this equipment. You might want to install something like a snow depth sensor, because you might have very deep snowpack in the winter. You have a snow pillow, which measures the weight of the snow. This is a precipitation gauge. Water falls into this, and you measure how much water is in there. And then you have the shelter, where you have your computer collecting the data, and then you probably send it off somewhere so you can use the data operationally. So you can imagine this is expensive to install, and then you got to worry about moose or bears or whatever knocking stuff over, and you got to fix it every year. So there's a lot of maintenance, a lot of expense here. Another way to measure snow is to go out, and manually stick a ruler in the ground, see how much snow there is. It's even more labor intensive. If you want to measure evapotranspiration, which is the total of the evaporation and the transpiration, the water that's going into the atmosphere from the land, the gold standard is to use something called a weighting lysimeter. So this is like, imagine there's a big scale. Well, there is a big scale buried underground here. It's measuring the weight of all this soil above it, and so you know how much water is stored in that soil. You're also measuring, you have a rain gauge somewhere around here. Somewhere they have a rain gauge here. You're measuring how much rain comes in, and you can measure how much water runs off. There's going to be a little drain at the bottom of this thing underground, and so you can do a little water balance on this and estimate how much water must have evaporated to account for the other changes. So again, this is really expensive to install, and so what they usually do is you have a few of these lysimeters around the country, and then you have these weather stations that use another approach. They're measuring fluxes of radiation, and you can use that to sort of back out an estimate of the amount of evaporation that would happen, and use the lysimeter to calibrate that. So you have more of these weather stations around. But again, those are somewhat expensive to install. If you want to measure the amount of water in the soil or soil moisture, which is important because this is the water available to plants, and it also is a lower boundary condition for the atmosphere. So if you think about how much water is going to evaporate and affect atmospheric processes, it's the water that's in the soil here. If you want to measure water in the soil, you can go out manually and make measurements. When I was a grad student, I made thousands of these measurements in Oklahoma. You stick this thing in the ground, and it reads out how much water there is. You can also install something that's more automated than that. surface water and river flow is fairly easy to measure. You measure the height of the stage, which is the height of the water, and you can relate that with other measurements. You can relate that to the amount of water flowing through. This, by the way, is Lake Mead, and this was back in 2004, and it was already way below its normal watermark, and now it's, right now it's something like 25% of its capacity. It's pretty bad. Groundwater, to measure groundwater, you have to drill a well into the ground, and then go out and make measurements. You stick a tape down there and see how deep the water is. This can be automated as well, but again, it's expensive to put these things in, and not everyone wants to have a monitoring well on their property. So the point is, ground-based measurements are expensive to install and maintain, and make measurements. And if you look at the around the world, where these measurement systems are installed, so these are meteorological measurements in the upper left. This is the global telecommunications system, and these are key measurements used for weather forecasting. You can see that in the U.S. and Europe, you have a fairly dense network of observations, but much of the world, you're looking like Africa, the interior of some of the continents. There are not very many observations, and really it's not adequate for a lot of the intended purposes. If you want to measure stream flow and river flow, again, the U.S. is really good. The USGS makes all these measurements, provides all these data. They're really valuable, and anyone can get them. Outside the U.S., some countries are good, like Brazil. They provide all their data and it's up to date. The darker blue color means that it's available more recently, like in the past year. As you get to, these are really hard to see, I'm sorry, but if you get to the lighter colors and the more the warmer colors, that means it's it was a long time ago that you can get the last measurement. So, for example, in the Nile River in Africa, Egypt never provides their data anymore. The last measurement you can get on river flow from the Nile is in the mouth of the Nile in Egypt is something like 1983. So a lot of these measurements just aren't. They're being made, but for political reasons, countries don't want to share them. And then for groundwater, this is the world up in the upper right. There are 8 countries that provide their groundwater data in yellow. It doesn't cover much area. The U.S. again is really good about it, but even the U.S., if you look at the observation stations that have a significantly long record that you can use for something like monitoring climate effects on groundwater, it's pretty sparse in the central and western U.S. Pretty good in the eastern U.S., but you're relying on perhaps one observation in Colorado. So there's some major gaps there. So that's part of the premise for why we do remote sensing. With remote sensing, you have a satellite flying around the Earth. There are no political boundaries. It can make measurements everywhere. You can provide global maps. And so these are some of the current and planned NASA Earth science missions. Let's see here. The primary operations, or the ones that are recently launched, are here in the lower left. And then all these ones with the white labels are called extended operations, meaning that maybe it had a 3 or a 5 year planned lifetime, but they've survived longer than that, and the incremental cost of keeping them up there is not that much. I mean, you get really valuable data, and it doesn't cost that much to keep them going. So yeah, we keep these satellites going, and then up here we have some satellites that are either in implementation, meaning they're building the satellite right now, or these are satellites that are scheduled. They're in formulation. We hope to launch them sometime in the next decade. And many of these are relevant to hydrology, and I'll talk about a few of those. So if you want to make one measurement, if you're a hydrologist, well, the answer is right here. If you're a hydrologist, what measurement would you want to make first? And the answer is precipitation. And that's really the key measurement for a hydrologist. So we have TRIM, the Tropical Rainfall Measurement Mission, which launched in 1997, and sadly it is finally on its final descent. It's got almost no fuel left. There's a tiny bit of fuel to avoid collisions with other satellites, and this thing's going to fall into we hope into the ocean sometime in the next year. But this thing has really been a workhorse for us. and so it doesn't go all the way to the poles, but for this area, it provides observations of precipitation that are better than anything we get from any other satellite. Fortunately, there's a follow-on to TRMM called the Global Precipitation Measurement Mission, or GPM, which launched earlier this year in February, and it's doing great. And it's nice that we have a little bit of overlap between TRMM and GPM, because then we can do some calibration, make sure they're measuring, their measurements are the same. And so GPM is one satellite, but it actually it uses data from a bunch of other satellites and is going to give us better coverage, and we hope better accuracy than TRMM did. And oops, click on this, see if it works. So this is showing during Hurricane Katrina, the white are just the clouds, the sort of visual observation of the clouds, and then you can see these are rainfall totals that are made using TRMM and other observations. So this is the kind of thing we can get from these satellite observations is how much rain fell there, and clearly we don't have precipitation measurements out in the ocean, so you couldn't do something like this without a satellite observation. And incidentally, you wouldn't have a weather forecast without satellites. I mean, you'd be going back to well, that cloud looks like a mare's tail, so it's going to rain tomorrow. These things are critical. MODIS is the Moderate Resolution Imaging Spectroradiometer, and that's on two of our satellites, two of our actually aging satellites, Terra and Aqua, that still chugging along, but we don't know for how much longer. And MODIS makes some really important measurements that's used with other observations for a lot of things. For example, snow cover and sea ice. And so this is an animation of, and you can look down here, this goes from 2002 to 2003, was it September to, I forget, sometime in 2003. Just showing how the sea ice changes and the snow, and you can see, especially mid-latitudes, you get snowfall. The snow will last for a little while and then it'll melt. Then you have permanent snow cover up in the northern regions. This here, where it was dark, that meant there was that's when it's permanent nighttime up there. Sometimes a year you can't make a measurement, and you can see how the sea ice changes too. These sea ice observations are some of those valuable things that contribute, that give us an idea of how much sea ice is there, and we've seen this long-term decline where every year, generally every year there's less sea ice on average, and eventually we'll be able to have trade through these northern routes here. Really valuable to the Navy. They're really interested in this stuff. SMAP is the Soil Moisture Active Passive mission, which is scheduled to launch on January 29th. And this is going to make measurements of soil moisture, which I mentioned before is really valuable for our weather forecasting and also agriculture and other things, drought monitoring, etc. And the surface water ocean topography mission is one that's still sort of in this conceptual phase. We hope this is going to launch in 2020. And this one is going to measure the height of water in big rivers. And the idea here is that you can relate the stage of the water, the height of the water, to the amount of water flowing through. And so I mentioned before, you don't have observations in the Nile. Egypt won't tell us how much water they're using. Well, guess what? 2020 comes along. We're going to have an idea what's going on over there. So this is going to be pretty cool. Gravity Recovery and Climate Experiment is the mission that I work on the most, so I'm going to spend some time, most of the rest of the time, talking about GRACE and its applications. GRACE launched in 2002, and what makes it really special is that while most remote sensing satellites are measuring either emitted or reflected wavelengths of the EM spectrum, so it's either sending a signal down and measuring what comes back, or just measuring the natural emission of radiation from the Earth's surface or from the atmosphere. And these are some of the different things you can measure at different wavelengths of the EM spectrum. You're limited, though, with this, that you can't penetrate below a few centimeters of soil or vegetation with this type of measurement. So if you want to measure groundwater, you're out of luck with this type of technology. But GRACE is really unique in that it's actually not looking down, it's actually measuring Earth's gravity field. And the way it does that is GRACE is actually two identical satellites that are following each other around the Earth. And what happens is the key measurement is the distance between those two satellites. And so imagine there's a gravitational anomaly, which means there's a lot of mass here. You have a mountain range. That means there's a lot of the gravitational potential is a little bit more. Not like you'd feel it, not like you'd stand in the mountain and say, "Ooh, I feel heavier here." But it's enough to affect the orbits of these satellites. And so when they're passing over a mountain range, the first satellite gets pulled forward, and this distance between the two satellites increases as they pass over. This first one's sort of held back, and the second one gets pulled forward, and the distance gets smaller, and then things even out later on. This distance between the satellites is roughly 200 kilometers. The satellites are about 450 kilometers altitude right now. So it's a 200-kilometer distance, and they're making measurements every 5 seconds or so of the distance between these satellites. And those measurements are precise down to the size of a red blood cell. So you're measuring 200 kilometers every 5 seconds down to the size of a red blood cell. It's a really incredible measurement. So over the course of a month, we can take all these measurements and put them in a big regression routine in a supercomputer and come up with a map of Earth's gravity field. And so that's what we've been doing. And the measurements are so precise that not only do we see the static gravity field, which are things like, that happen over very long periods, like building of mountain ranges, et cetera, we can also see changes in the gravity field. And those changes in the gravity field are caused by changes, basically three things. There's changes in atmospheric mass, so atmospheric pressure. There's mass in the atmosphere, the ocean circulation and tides. That's a huge amount of mass moving around. And then over the land surface, the changes in terrestrial water storage, the groundwater, soil moisture, snow, and surface water are the biggest contributor or the largest mass variations that cause variations in the gravity field that GRACE observes. So what we can do is we can estimate the atmospheric contribution to mass changes, and we can estimate the ocean contribution, strip those out of the signal, and what's left are changes in gravity that are caused by changes in terrestrial water storage. And so what that looks like here is, so here are the components of terrestrial water storage. And if you look at the state of Illinois, which is one of the few areas of the world actually where you have enough ground-based observations to make this sort of a time series. This is a time series of terrestrial water storage where the blue is groundwater, and this is an equivalent height of water in millimeters. So if you imagine you took all of the groundwater and you brought it up to the surface, how does the depth of that change over time? Same thing with the soil moisture, which is shown in red, and snow in white. So for Illinois, snow is not a big contribution. So you can see in Illinois, the soil moisture variations are the largest component of the terrestrial water storage. The groundwater is also big. Surface water is actually even smaller than the snow. But other parts of the world, you go to alpine areas or northern areas, snow is going to dominate the terrestrial water storage signal. In the Amazon, surface water is the dominant component. And GRACE is only telling us the total, okay? So GRACE can't separate the groundwater from the soil moisture, et cetera. It's just telling us this total, and it's up to me as a hydrologist to try to figure out, okay, well, there's a total terrestrial water storage change of X. How much of that was groundwater, for example? The other thing GRACE can't do, it cannot tell us the total quantity of water. It can only tell us the changes. So I can't go out and tell you how much water is left in an aquifer, for example. I can only tell you how that's changing in time relative to the long-term mean. So this is what it looks like if you animate these monthly terrestrial water storage anomalies. So again, an anomaly is if you have the long-term mean water storage, long-term average. The anomaly is how much the departure from the mean, how much does it change? So here we have blue regions mean there's more water than the average. The red means there's less water than the average. And so you can see that there's a natural seasonal cycle. So if you look at the South America, for example, there's a huge seasonal cycle where it gets, they have a dry season and a wet season. Nothing surprising there. But if you take away that seasonal cycle, so we can take an estimate of the average seasonal cycle and subtract that, what's left are these non-seasonal terrestrial water storage anomalies. So these are things like droughts and pluvial, which is a fancy word for flooding. So the sort of the non-seasonal component of terrestrial water storage variations. And this is really some of the really interesting stuff, is trying to explain, well, what's going on here. And much of it relates to things like El Nino. You know, El Nino has big effects on the water cycle. You know, atmospheric circulation changes, and you get weird things happening like polar vortexes, but you also get, you know, more rainfall in some area. You know, a lot of this is just sort of natural variability. So looking at let's look at some of the trends in global freshwater storage. So we have a time series from GRACE. GRACE, again, launched in 2002. So we have data from then until now, and GRACE is still chugging along. For each location on Earth, we can look at the time series, and we can fit a linear trend. Say, how has water storage changed from 2002 to present? And this is what the trends look like when you map them. So again, yellow and red means that you're losing water in centimeters per year, and blue means you've been gaining water during this time period. And so you know, I put the trends in parentheses because in quotes because this is mainly, you know, a lot of this is natural variability. Okay, so it's not like I'm going to say these trends are going to go on for the next 10 years. Over the next 10, 20 years, a lot of the trend areas will become sort of a green. It should average out over time, but not everywhere. And so those are the interesting things. So one of the first things we can do is say, well, where are we using a lot of water? What are the direct human impacts? And this is a map of irrigated areas. Sorry, the colors don't come out very well. This is another estimate of net consumptive use of grounded surface waters in the upper right. And if you look at the areas where there's a lot of irrigation, basically, you'll see that those tend to be the areas where we're seeing a reduction in terrestrial water storage over time. So, clue there. Now we can focus in on some areas of interest here. So let's look at India, and this is one of the first regions we studied back in 2008, 2009. And we had a publication that came out in Nature, and we were looking at this 3-state region of northwest India where they use a ton of water for irrigation. You know, they're irrigating wheat and rice, and when you do that, you're pumping a lot of water out of the ground, spreading it on the surface, and most of that water evaporates. And guess what? You know, you're in a semi-arid part of the world. That water's gone. And so, when we plot the time series, the black line is GRACE alone, the total terrestrial water storage. From models, we can estimate the soil water storage changes, and you can see those are pretty stable over time. We subtract the soil water from the groundwater. Those are the main two components in this area. I'm sorry, the soil moisture from the terrestrial water storage. We get groundwater, which is in blue, and you can see it's sort of like a tennis ball bouncing down the stairs. When you get ups and downs, there's a seasonal cycle there, but generally the trend is down. So that's the equation we use. Where the groundwater is the total water storage, terrestrial water storage minus the soil moisture minus the snow. Really no snow there, so if you subtract the soil moisture, this is what you get. And so we estimate that the rate of depletion is somewhere in the neighborhood of 16 to 17 cubic kilometers per year. And to put that in perspective, Lake Mead is the largest reservoir in the U.S. And when it's full, it's supposed to hold about 35 cubic kilometers of water. So this area alone, every 2 years, they're using a Lake Mead worth of water, and it's gone. Okay, it's not being, that's what's not being replenished. So it's a pretty scary situation in an area where over 100 million people live, and it's even worse if you look at this larger area. And by the way, data scarcity is not an issue in India. Okay, they have data. They are measuring their aquifers. The issue again is that they don't provide those data to everyone else. So they sort of, the government kind of knows what's going on, but they don't necessarily want to say, hey, we're in big trouble. But we can see using our satellite observations that they've got a problem there. Okay, another area to look at, Middle East. I think it's really interesting. If you focus on this one region in northwest Saudi Arabia, and this is 1987. This is a Landsat image. Just looks like a normal image from Landsat. In 1991, you start to see these funny patterns going on the ground, and then by 2000 you see a lot more of them, and then 2012 they're all over the place, and it looks very similar to what you see when you're flying over Kansas and you look out your window, the airplane, these crop circles everywhere. This is desert, okay? I mean, there's no rainfall there, so this is all this this crop production is from pumping water that infiltrated, that recharged, many thousands or hundreds of thousands of years ago. And once you pump that water out and it evaporates, it is gone. I mean, you are not getting that water back, no matter how careful you are with your use. So I mean, it's great for them now. They're able to do a lot more crop production than they did in the past, but it's completely unsustainable. So if we use GRACE to look at this area, you see there's a bullseye there. Focus in on this bullseye, and we can do the same thing we did with India, get this trend in groundwater storage, and our preliminary estimate of the groundwater depletion rate is about 2.6 cubic kilometers per year. Let's look at the North China Plain, another area where we see one of these bullseyes. Again, a lot of agriculture here, a lot of people to feed. You pump groundwater out of the ground. You can increase your crop production, but if you're doing it at this rate, it's not sustainable. So about 5 cubic kilometers per year we're estimating for this rectangular region here in the North China Plain. It's, again, unsustainable over time. So this shows some of the trends, and I'm sorry that it's hard to read a lot of these things, so I'll go around, show you, try to explain some of the things that we've seen with the GRACE data. So red are areas where, let me start with orange. So orange are areas where we've seen a trend of depletion, but we expect that there's, just part of the natural variability. It's probably going to, bounce back sometime over the next 10 or 20 years. It should come back to normal. Blue areas, similarly, are areas where there's been a trend of increasing water storage. Again, that's part of the natural variability. We expect that over time that's probably going to bounce back to being a green, which is the zero trend. But the red areas are areas of concern. So red areas are either, for example, Greenland, where the ice sheets are slowly slipping into the ocean, and you have this huge trend of depletion of the ice sheets on the order, based on GRACE data, it's on the order of 142 cubic kilometers per year, ice slipping into the ocean. Similarly, in the West Antarctic Peninsula, a lot of water, a lot of ice sheet flowing into the ocean. It is interesting that in other parts, eastern Antarctica, they've actually had some increase in the thickness of the ice sheets. And we think that's related to shifts in atmospheric circulation in the area. Here up in along the coast of Alaska, these are glacier. This is caused by glacier melt, and that's a huge trend on the order of 84 cubic kilometers per year. And then there are other areas I showed you before, like in the Middle East, where most of this depletion, or some of the depletion, may be caused by drought, but a lot of it's being caused by use of water resources, either surface water or groundwater, being used at an unsustainable rate. Most of it evaporates in these dry regions, and then it's gone. So that's really cool, but we can do better than that. We can combine the GRACE data with other observations, and so we have these land surface models, which are numerical models. It's sort of like the land component of a weather climate forecast system, where we have a pretty good understanding of all the physical processes that happen. We have equations that describe those processes, and so we can run a model that uses as inputs things like precipitation and solar radiation. What are the inputs of water and energy on the land surface, and the model determines how much of that water runs off into streams, how much water percolates down to the aquifer, how much water evaporates or is used by the plants. And then we can divide up the world into a grid, do this everywhere, and come up with some pretty good estimates of things like soil moisture. And so here, with our land surface models, the inputs are, we have static inputs, things like the vegetation type, soil type, elevation, what we call the forcing fields, or the time variable inputs. These are usually meteorological fields that we get either from direct observations like precipitation and solar radiation, or they come from atmospheric analysis models that NOAA runs. And then we get output fields, things like soil moisture, snow water equivalent, evaporation, transpiration, et cetera. And so these are valuable pieces of data that we wouldn't have otherwise. And so we can use these land surface models to integrate all the data we have. Again, I showed you the picture of all the different NASA satellites, and one of the questions is, well, how do we make use of all these different types of data? A lot of them are not measuring exactly the property that we want to know about. They're measuring something that's related, or maybe there might be some big gaps, either spatially or temporally. But by combining all these data within a model, you can sort of constrain that model and make sure it stays on track, and use all the data to sort of confirm each other. And so we do things like we can use the best precipitation data we have, the best solar radiation data we have, use those as inputs. We have measurements from other satellites of things like snow cover that can be used to then constrain what the model thinks is going on with snow. And we have ground-based observations to validate all this, to improve the model, and so we end up with a result that's better than any of the inputs we had to begin with. I think I'm going to skip this, but the point is that we do this globally, and if you go to this website here, this is where we serve these data, and we have something in the order of between 400 and 1,200 unique monthly users. So every month, between 400 and 800 people are actively downloading these data, and we can't collect information on who they are, but we have some idea that a lot of them are people who are interested in agriculture. There's also a lot of students that use the data. Scientists use it for other things, weather forecasts. So there's a huge range of things these are used for. So again, I showed GRACE is pretty low resolution. This is GRACE on the left, and I'm just comparing this with the U.S. drought monitor, which is what you see in the back of USA Today sometimes, looking at the drought that happened in the southeastern U.S. back in 2007 and 2008, and so GRACE and the U.S. Drought Monitor are pretty much in agreement on what happened there. But I want to make the point that, so again, GRACE is pretty low resolution, but if we assimilate it into one of these land surface models I was showing you, we can get results that are much higher resolution, both spatially and temporally. And we can also divide up this total terrestrial water storage into surface soil moisture, root zone soil moisture, and groundwater. And then if you compare those with again, this U.S. Drought Monitor map, which is based on, to produce this map, there's a group of authors who rotate and who produces the map each week, and they all have a big telecon on Tuesdays, and they discuss what data has come in. It's mainly precipitation data, but there's also other information from state climatologists, and they basically take this map, and every week they move these lines around a little bit, and it's really important because a lot of the emergency funding for drought actually is based on what the Drought Monitor authors say. So what we've been able to do is provide a new source of data. Previously, they did not have useful information on groundwater, these few wells, but we can actually provide a map of what's going on with groundwater, and that's one of the things they use as an input every week. So if we take our weekly maps that we're producing, and we have this, see the timeline down here in the lower right, wetness percentile there. And the wetness percentile is basically relative to 1948 to present. How dry or wet is it relative to the time of year and that 65-year period. And so, for example, if it was at 10, that would mean that it would only drier this time of year 10% of the time. We can see some things like we just passed there was a big drought in the southeastern U.S. As we get into 2011, you're going to get really wet up here. You might remember there was a bunch of flooding in north central U.S. in 2011. I want to point out the left is root zone soil moisture, the right is shallow groundwater. So the soil moisture, because it's closer to the surface, varies much more rapidly. The groundwater sort of integrates over time the meteorological inputs, and it varies more slowly. So it's actually a more useful drought indicator. Let's play that again. So again, just to point out some of the things that are happening here, drought's a natural thing. You can see how it varies in time. We have wet periods and dry periods. That's all pretty normal. As we get into 2007, pretty soon, you're going to start to see the drought develop in the southeastern U.S. So you see that big drought signal there. And then we'll get to, when we get into 2011, watch for that big wet signal in the north central U.S. Remember 2009, 10. All right, it's starting to get wet up there. Starting to get real wet, and they're flooding. Okay, and then watch in 2012. This is when we had a huge drought that covered almost all the continental U.S. 2013, it starts to subside more or less. But look at California. Look how dry they are, especially in 2014, and they're just getting hammered at the end there. So just to summarize what I've talked about, these space-based observations are critical. I mean, we can't do everything with ground-based observations. And one of the reasons it's important is because, monitoring the water cycle is important is because one of the most noticeable consequences of climate change will be impacts on the water cycle, the fresh water that's available to us. NASA's GRACE mission is unique. It's able to monitor all forms of water at all depths. You can't do that with any other remote sensing observation. You see these emerging trends in terrestrial water storage, and we can sort of divide those, we categorize those as natural variations, climate change impacts, or direct consequences of human activities such as irrigation. We can improve the value of the GRACE data by combining with other data sources, particularly remote sense precipitation, et cetera. And by the way, the GRACE mission sort of running on fumes at this point, still chugging along, still giving us good data. But it's not gonna last forever. But fortunately, the GRACE follow-on mission, which will be very similar to GRACE, a little better, is going to launch in August of 2017. And I'll leave it at that. These are some websites that have some useful materials if you're interested. And I'm happy to take any questions. Yeah. Yeah.
Okay. I have two questions. One is when I go out west and I see those huge shooting irrigation sprinklers, are they making any headway in getting those types of irrigation machines to be less, have less?
Yeah, absolutely. So they're always looking for ways to conserve water, especially as there start to be more regulations about, they can only use a certain amount of water. And so first thing is, instead of spraying the water up in the air, you spray it straight down. I used to think that they were smart enough to do it at certain times of day, like at nighttime when it's not going to evaporate, but it turns out they actually run those things just nonstop throughout the growing season, wet or dry, whatever, until their allocation of water is used up. But one of the big things they're doing is drip irrigation. So drip irrigation is where they take this little, like a sort of a hose with it's perforated hose, and they roll it out along the, between the crops, and it just lets a little bit of water percolate out, and those have huge water savings. So those are great things. Obviously, the drip irrigation is a little more work for the farmer, and maybe a little more expensive to get started. But I think as the pressures increase on fresh water, that's the way things are going. Which, so it's good. Yeah.
So my second question is, can you shed any light on why there's so little monitoring of groundwater out west?
I mean, so the map I showed you is what's available from the USGS. That doesn't mean that people aren't making measurements and just holding on to them. If I were a farmer, I'd have a well and I'd make measurements in that well. And it's a little harder to do that because if you're pumping out of the same well where you're making measurements, then it's hard to get an estimate of what the sort of ambient groundwater level is. But yeah, I mean, I think that's the bottom line. Is there are measurements being made, it's just the availability of them.
And can you shed any light on why the government isn't doing more, or why we can't?
Well, the government's limited in what they can do. I mean, there are property rights, and it varies from state to state. Water use varies a lot. Some places if you have a plot of land, it could be 4 feet by 4 feet. You dig a well there, you can pump as much water out as you want, no matter what the impact on your neighbors. Other areas, they're starting to be a little more careful with their water, but you might,
Back east is where all the monitoring seems to be happening, and there's more water there.
I think that's more of a depends more on how populated it is than how willing people are to share the data, I guess. Yeah.
May I repeat the question?
Oh, I'm sorry. Yeah.
Would you repeat the question so that everyone can hear it and we can get the web?
Okay.
Thank
Okay.
you.
The first question, which was about more efficient irrigation practices. The second question was about why is data not more available in the western U.S. Yeah, go ahead.
Just first a comment and a question, just to help answer your question. You can go to California and find thousands of well data on California Department of Water Resources. So it depends state by state. You have to look for it. You're right. USGS has set a certain level of monitoring for the states, and that quite a bit.
By the way, the map I showed was the wells that have a long enough record and a frequent enough record to be really be useful for sort of looking at how groundwater varies in time. But there are a lot more well observations available from the USGS, but they might just be like one measurement per year or one measurement ever. Yeah, go ahead.
A good segue to my question is that given that GRACE is only 12, 13 years old, how robust are your trend analyses, given that there's a number of natural cycles that are shorter and much longer than what you're seeing in GRACE? How do you make longer predictions, if you will, with such a short time?
So the question was how robust are our trend estimates given that GRACE only launched in 2002? And the answer is, I mean, they're not robust. That's why that's why I called it emerging trends. So we can't say, I can't predict with any certainty that anything's going to continue at that rate. But we have auxiliary information, independent information that tells us more about how long has this been going on, and is it normal? Is it expected to be part of the natural variability or not? And so something like the rate at which Greenland is losing ice into the ocean, there's a lot of other information that corroborates that's it's never happened at this rate before. I mean, they've never seen anything like this. So that type of information is useful in the areas where it's groundwater depletion. We know that they're using more and more groundwater, and we know what to some extent what it looks like when you get a lot of rain. We know it can recharge, but these are normal years. These are years when if you take out the variability caused by different amounts of precipitation, that this isn't it's not declining in a dry year. It's declining in a normal year or a wet year. That tells you that there's something else going on besides just natural variability. Yeah.
I was wondering, with the non-replaceable aquifers, can you monitor those, like especially in California, the Central Valley, which is dependent on aquifers, which are cold, are being pumped out and won't be replaced? Can you tell how much water is there and how fast it's being depleted?
Yes. So the Central Valley is an interesting. The question was, can we monitor groundwater depletion in the Central Valley, these non-replaceable aquifers? And the answer is yes. It's a bit of a special case because you go to the Central Valley, there are tons of wells. I mean, you don't really need GRACE to tell you what's going on in the Central Valley so much. But that said, you could use GRACE alone, and we've shown that it very much agrees with the ground-based estimates, and so part of the issue there is it's the simplest to interpret GRACE when there's a change in the shallow unconfined aquifer. When you drill down to get to the water table. When you're talking about a confined aquifer that's really deep, GRACE is still going to measure mass changes in that aquifer. But what might happen, you might have this aquifer that's under these bedding planes where there's you might have a clay layer above and below, and the thing actually outcrops hundreds of miles away, or and that's where the recharge is happening, and the recharge is flowing in, and so you actually have changes in the water table way over here caused by pumping water here, and because it's a confined aquifer, the water level's not actually going down, it's actually going down somewhere else. So it's a bit of a complicated situation, but the bottom line is we're seeing the depletion. It might be not quite exactly where the pumping's happening, but we can definitely measure it. Yes?
I am wondering, is anyone working on maps which are linking the education, which is even more tailored than what you're talking about today? I'm totally convinced. But I can see countries where they're having a lot of water issues and the irrigation is just making it worse. but the cultural values, people are, maybe they didn't hear in elementary school about the water evaporation, or maybe there's so much smog that they're linking water in the air to helping with the smog. Anyway, I'm talking about tailored education to that particular country, and whether those countries are getting it, whether it's from schools or government outreach groups, and then any changes in trend. I'm talking long term. I mean, I'm trying to think of a solution here that's beyond what we're talking about right now. Is anybody talking about educational outreach?
Okay, so the question was, is there any sort of educational outreach to try to educate people on what's happening with their groundwater? Is that sort of the idea?
How does a good solution such as the irrigation drip, because in my opinion, it's not enough to talk about just this, but also an alternative such as the irrigation drip.
So I guess my answer would be that when you look at where the major depletion is happening, it's usually caused by irrigation. So you can educate the populace about it, but it doesn't necessarily translate into any sort of change in behavior. And I think that the change in behavior is probably going to happen when it's some sort of an economic stimulus, or some sort of regulation. So, for example, in northern India, for a long time the government gave them, I think this is starting to change, but the government was giving them free electricity to pump as much water as they wanted, because they wanted to maximize the agriculture. And so the result was there's no incentive to save water at all. I mean, your neighbor farmers are all using a lot of water. So if I use less water, I mean, how is that going to help? My aquifer is still going to be depleted by my neighbors. So I think really in that sort of situation, it has to come down to some sort of government incentive, or to use less water, or disincentive to use a lot of water. Starting with not providing the free electricity, but I think that may be the better way to go, rather than hoping that if they understand what's going on, that there's going to be a change. I'm skeptical that it's going to make that much of an impact. Yes.
Just to go back to California for a second. Obviously, they're in the midst of a very severe drought. I guess arguably unprecedented. When you have the map up of the trends adjusted for natural variation, it looked like California, or most of California at least, fell within that green zone that would average out over time. And sort of what we know, what we hear a lot about climate change, is how these things, these types of droughts will become more severe and more frequent as climate change progresses. Can you just expand a bit on that and talk about what goes into that determination?
Okay, so the question was basically that California looked like it was sort of green when you look at the trend map, and you wanted me to explain sort of what goes into to our understanding of the trends in different regions.
Yeah, why you still have that as sort of evening out.
Yeah. Okay. So for the case of California, I think I mentioned that the spatial resolution of GRACE is pretty low. So basically, it's averaging over a very large area, and even the sort of, if you could pick out a pixel in some of those images I was showing, that's sort of an artificial pixel. That the spatial resolution of GRACE is on the order of its smallest about 200,000 square kilometers. So the state of Illinois is about 450,000 square kilometers. So you can measure something like the size of the state of Illinois, or maybe half, with GRACE, and it's really hard to focus down on a smaller area. And most of that depletion is happening in the Central Valley Aquifer, which is this narrow band, which is about something about 50,000 square kilometers in Central California. And so even though there's that big depletion going on there, it sort of gets smoothed out when you look at it with GRACE. It's sort of like, you put on your grandmother's glasses and everything looks fuzzy. I mean, that's sort of how it is with GRACE. But when we focus in on GRACE, I showed you these global maps, and when we focus in with GRACE on California or the western U.S., we can do a little better than what I showed you with those global maps, and we do actually see the trend there, and it's pretty much in agreement with what what we get with the ground-based observations. I don't know if I answered your whole question or not there.
This has been a presentation of the Library of Congress. Visit us at loc.gov.